Hey guys, how's it going, everyone?
Going great. How was you?
All right. Mm, all right. So one thing with the videos, so some of you brought it up that you're having troubles accessing the Zoom recordings. So what I did, I downloaded the Zoom recordings and put them on YouTube. So has anyone tried to open the YouTube videos? Do they work? Like if you go to your weekly modules now on Canvas, you should be able to find them just in the modules with like YouTube links. But let me know, guys, if that doesn't work. And it'll probably be a little bit easier for you to do. Did anyone try to look at them yet? No? All right. Well, I mean, let me know if you guys have any troubles with the videos. Well, I guess one more thing so this week we're not going to have the quiz, but we do need to do our first midterm. All right, so we will have the first midterm. I think I already forgot. So I know it's going to be due October 9. The midterm one is due October 9. I think it opens up October 2nd or something like that. Or let's just say it opens up October 2nd. No, I'll change it later. So your midterm one is going to be really similar to your quizzes. So just like in quizzes, you're going to open it up, you're going to see all the questions, you're going to do it on your piece of paper, and then you're going to scan it and you're going to upload it. Is anyone still having troubles with uploading quizzes? I think most of you seem to be okay, at least from grading the quizzes from what I've seen. All right, on your midterm, it has like 9 problems on it. And you will have, so this midterm, I mean, if this was an in-class midterm, this would be like an hour and a half long midterm. So I am going to give you 4 hours in case you have any problems with like uploading things. All right, but I mean, we can't really do more, right? Because it's supposed to be like an hour and a half long exam. But so you will have 4 hours, right? So be careful, once you open it, you'll have to submit your work within the 4 hours, right? But you can do it anytime within the week, right? Whatever time you feel is convenient. But maybe don't start it just yet because midterm 1, so it will cover chapter 1, and then it will cover the first 3 sections of chapter 2. So like 2.1, 2.2 and 2.3. So we're going to finish 2.3 today. All right, so those sections will be on your midterm. How to study for it? I mean, I'll go over all the quizzes. If you guys have a book, you can do some like exercises from the book, or you can go over your homework problems. I mean, if you are doing all of the homework problems online, like I mean, you should be perfectly okay. And again, you are going to have 4 hours. It's like 9 problems. 4 hours, it's like 20, 25 minutes per problem. I mean, some of the problems are not very long. So I guess I think you guys should be okay. But any questions on midterms? You can find it in your module, I think for this week. So in week 6. All right, so we do need to do the midterm now-ish because we're supposed to have 3 of them, right? And we're kind of running late with the first one. Any questions? Nope. You're doing okay. All right, but so the goal for today, we need to finish everything through like 2.3. I think we should be able to do it. All right, so just to review last time, what did we do? So we started talking about inverses of a matrix, right? So we did 2 things. We kind of looked at, well, the one important thing is now we're not looking at m by n matrices, we're looking at square matrices. So a matrix has to be square for the inverse. So square matrices. So we'll go back to m by n matrices, but for inverses, we're just looking on the square matrices. Right, so and we define the definition of the inverse, right? So inverse of the matrix is such a matrix C such that if you multiply it on the left to A, or if you multiply it on the right to A, which you're getting back as your identity matrix. This is kind of an equivalent of 1. So this is a definition of your inverse. And so for all the square matrices, you either will have an inverse, so A would be called invertible and non-singular, or you will not have an inverse. The inverse does not exist. And then the matrix is called non-invertible or more shortly singular. And that was some notation. Then we did one theorem which said that, well, if the matrix is invertible, then for all B and Rn, my equation X equals to B will have a unique solution, right? And this just follows directly from the existence of inverse, because if my inverse exists, I can take my equation, I can multiply by A inverse on the left, then A inverse times A is I, which is equivalent to 1, which will give me X on the left-hand side. And then on the right-hand side, I just have the formula for my solution. Right? So I have I, A inverse times B, I times X becomes X, and X equals to A inverse times B. All right, so I mean, basically what this is if A is invertible, then I can use the same algebraic rules as I use for real numbers, sort of, right? Like for real numbers, I would just divide by A or multiply by A to the minus 1. So with matrices, I'm doing the same thing. But my matrix has to be invertible for this to hold. And then we did some formulas, right? So if A is invertible and B is invertible, then the product is invertible. So product of invertible matrices is invertible. And we had the formula that the inverse of AB is B inverse times A inverse. Remember, we like multiplied it to show why we need to reverse the order of A and B here for inverses. All right. We also showed that A inverse is A, right? So basically taking an inverse again gives you back your original matrix. And then with transposes, right, A inverse of the transpose is the transpose of the inverse. So we did those 3 last time. And then we also did for 2x2 matrix, a very simple case, right? So this only works for 2x2 matrices. There is a little formula for an inverse. So if I had A with components A, B, C, D, we defined what's called a determinant, and we'll talk more about determinants in chapter 3 for general matrices, but for 2x2 matrix, the determinant, and you can look at diagonals, you have positive and negative. You multiply A times D and subtract B times C. So what's nice about determinant, it will always tell me if my matrix is invertible or not. If it's not equal to 0, then matrix is invertible. Then I can go and start looking for A inverse. But if determinant is 0, then it's singular. So I can't find an inverse. And if it is invertible, then I have a nice formula for A inverse just based on the entries of A. I'm switching my diagonal entries, AD places, and then off diagonal entries, I'm just making them negative. And at the end, I'm just dividing by my determinant, right? Which is also the reason why I can't, if this equals to 0, I can't divide by 0, right? So even if you didn't check this prior to computing A inverse, I mean, you would get an undefined quantity here, right? If determinant is 0. You guys have any questions from last time? So that's kind of a recap of what we did last time. All right, so for 2x2 matrices, we know how to find an inverse. So now how do you find an inverse for 3x3, 4x4, and so on matrices? And there's a lot of different ways to do it, but kind of the most basic way and kind of the way that gives us the most insight into kind of how all of those things are related is basically going back to my elementary row operations. And now, instead of looking at just row operations, we're going to look at how do we perform those elementary row operations by using matrix multiplication. And it turns out that what you can do is you can use what's called elementary matrices. So we have 3 elementary row operations, right? Multiplying row by number, switching rows, or adding a multiple of one row to another row. So we'll have those 3 different types of elementary matrices that perform those operations. And it's really easy to construct them. Really what you have to do is whatever operation you're trying to do, you have to do it on your identity matrix. So if you take identity matrix of appropriate dimensions, so if A is n by n, you take the n identity matrix. And whatever elementary row operation you want to do, you do it on your identity matrix. So for example, here, if I interchange row 1 and row 2, I'm taking identity and interchanging row 1 and row 2 in my identity matrix, right? So this used to be row 1, now it's row 2. This used to be row 2, now it's row 1, all right? And now if I take any matrix A, so I just put some letters for elements of A, 3 by 3. If I multiply this matrix on the left, what it's going to do, following the multiplication rule, right? We're always going row by column, right? 0, 1 times D, 0, right? D. So 0, 1 times E, H, right? E, 0, 1 times F, I, right? So because I have the 0, 1, 0, what I'm doing is when I'm filling in my first row, the only non-zero entries are going to be the entries from the second row, right? So this is how my DEF moves up to the top. And then when I'm multiplying this row by all 3 columns, I'm basically filling the second row in my resulting matrix, right? And when I'm multiplying 1, 0, 0, I'll basically have A, everything else is 0, B, everything else is 0, C, everything else is 0. So my first row is actually moved in the second row position. Right, and here my third row is unchanged. Does that make sense? Yeah. So basically what I did, I interchanged my row 1 and row 2. So multiplying row by number, again, what I'm doing is whichever row I want to multiply, if I want to multiply row 3 by 3, I'm just replacing one of the ones in a diagonal with 3, and because I want row 3, I'm replacing 1 with 3 in row 3. All right, so I'm doing elementary row operations on my identity matrix, and then multiplying on the left. All right, and so again, just maybe do it yourself to kind of get used to how things are related, because again, every time you're multiplying a row and you're trying to fill the row in the resulting matrix, you're going through columns, right? So you'll have 1, 0, 0, A, 1, 0, 0, B, 1, 0, 0. So only the first entries survive, right? So this is the same. Second row would also be the same, because when I'm filling in second row, only the second, or D, E, and F will be multiplied by 1. The rest is 0. And then the third row, when I'm filling it in, right, I will have A times 0, D times 0, 3 times G. So 3 gets multiplied only by the third row. And then the very last one, when I'm adding a multiple of a row to another row, if you look at your elementary matrix, again, it's just, I'm starting with my identity matrix, right? And then again, just think of when I'm going through my rows, this will fill in the row in my new matrix, right? And I'm basically going through all of my columns. So this -4 will always get multiplied by an entry in the top entry in each column, right? And the second entry in each column would be multiplied by 0, and the third entry in each column would be multiplied by 1, right? So my last row here is filled in with basically -4 times A plus G, -4 times B plus H, 1 times C, 1 times I minus 4C. That makes sense? All right, so again, I did elementary row operation, I multiplied it by my matrix, and that performed my same elementary row operation on my matrix. But be careful here, because everywhere here I'm multiplying on the left, right? If I was multiplying it on the right, I am going to get a defined result, because I have 3 by 3, 3 by 3, right? I can multiply right or left. But with left multiplication, you are going to be doing something different. So if I took the same matrix right here, which is supposed to interchange row 1 and row 2, right? And now, instead of multiplying it on the left, I'm multiplying it on the right. So what's going to happen in this case? Again, if you're doing row by column, I would have B, then I would have A, then I would have C, right? So now I have BAC, and that's not any one of my previous rows that I had before. But if you examine it closely, I mean, what happens here is instead of interchanging rows, I'm going to actually interchange my columns, right? So in this case, if I multiply on the right, instead of interchanging rows, I'm interchanging columns. And in general, that's not going to be very useful right now, right? Because if we're dealing with systems of equations, I mean, I can't interchange columns, right? That mean I'm interchanging kind of coefficients of different variables, right? So you don't really want to do that. The same here. So if I took the same matrix that multiplied a row by 3, and if I multiplied this matrix on the right, again, I would not get what I want, right? Because now I would be multiplying not the last row, but the last column by 3. All right, so we're not going to do right multiplication. It has to be left multiplication in this case, but I'm just bringing this on as an example to kind of warn about this. So it does matter which side you multiply your elementary matrices on. Makes sense? So here kind of recap, right? So elementary matrix, definition from your book, that it performs elementary row operations on A by left multiplication, like we talked about, right? And your elementary matrix is always just created by performing the same elementary row operation on identity matrix I. Right? And here you can also note that row operations are always going to be reversible. So for each one of those elementary matrices, you are going to have an inverse, right? And we'll see this in the next example here. Right? So how would I find an inverse? I mean, you can just think of it conceptually, right? So if this elementary matrix, right, I have the third row modified from the identity, right? I introduced this -3, so I'm now basically working with the third row, and I'm modifying it by adding -3 multiplied by, since it's the second column, this would be the second row, right? So I'm subtracting 3 times row 2 from row 3. That makes sense? So conceptually, if I wanted to undo my subtraction of 3 times row 2 from row 3, I would just have to add back 3 times row 2 to row 3, right? So all you have to do, I mean, the best way to think of to do this, I think, is just conceptually, right? Undoing subtraction of row 2 from row 3 is adding 3 row 2 to row 3. So in terms of elementary matrix, then you just have to put +3 in this position, because you're working with third row and you're adding 3 times row 2, so 3 is in the second position to row 3. Right? And you can check, right? So how do we check? Well, if they are inverses of one another, then the product should be equal to the identity matrix, right? And here it's pretty easy to do, right? Again, I'm doing row by column, 1 times 1, 0, 0, 0, 1. Then 1 times 0, 1 times 0, 3 times 0, 0. 1 times 0, everything else 0, right? 0, 0, 0, 0, 0, times 1, 3 times 0. So 1, 0, right? And then 0, 0, 0, 0, 0. Well, no, the second one. Okay, 0, -3, +3. So this 0, -3, +3 will cancel out my 3's, right? Because I have 0, -3, and +3. So this gives me 0. So this undoes what I did with subtraction of 3. And then the last one is 0, 0, 1. So I do get my identity matrix. These two guys are inverses of one another. And the same thing you can do is like another example for if I multiply row 2 by 2, I would put 2 in my identity matrix in the second row. If I want to undo multiplication by 2, then I just have to divide by 2. So my inverse would be identity matrix with 1/2 instead of 2. And again, you can check this, right? I mean, what will happen is everything again is 0. And when I'm doing my second row and second column, I would have 2 multiplied by 1/2, so which will give me 1. So again, I'm getting my identity matrix. That makes sense? Yeah. All right. That's what our identity matrix is. So and then a little theorem, right? I mean, we mostly need those identity matrices to kind of understand things about when inverses do exist, right? I mean, in practice, I mean, you can use them, but still, we're basically just usually using like this row elimination, like we did before. So we have the theorem. If I have a square n by n matrix A, and that matrix is invertible, if and only if, right? So this is both sides implication. A is row equivalent to In. And in this case, any sequence of elementary row operations that reduces A to In also transforms In into A inverse. So we'll kind of dig into this a little bit. But basically, this means that if A is invertible, I mean, this is equivalent to saying that A is row equivalent to In, all right? And we'll basically just look at this in terms of matrices. But first, if I want to prove this, we have to prove in both directions, right? So if we first assume that the matrix is invertible, right? If A is invertible, then we know that AX equals to B has a solution for all B, right, in Rn. And we know that from the theorem that we did earlier, right? If A is invertible, then we know that I can always write down the solution in terms of the inverse, right? And in terms of the matrix, if this always has a solution for all B, that means that A is onto, and if A is onto, A must have a pivot position in every row, right? Because if A has pivot position in every row, I'm never going to have like a row of zeros and something that's not 0 in my augmented column. So the system is always consistent. Yeah. And now, because also A is a square matrix, so it's n by n. If A has n rows, and it has a pivot position in every row, since A is square, then we must have a pivot position in every column, right? If A was not square, maybe I have something like this with a free variable here. But if A is square, I mean, I'm kind of squeezed into having my pivot position everywhere in the diagonal, right? Because A is square, right? And this is going to be pretty important because this for square matrix is n by n because I have n rows and n columns. This fact will actually connect our concepts of matrix being 1 to 1 and matrix being onto. They would actually be equivalent, but we'll get to it in a little bit. But in our case, okay, we're just using the fact that this system has a solution, which implies that I have a pivot in every row, because A is squared, that also implies I have pivot in every column. So my pivots are all along the diagonal. And if I have pivots all along the diagonal, remember when we were doing solving systems, that means that when I start getting to my reduced row echelon form, all the pivot positions will have ones, zeros above, zeros below. So my reduced row echelon form of such an A is going to be an identity matrix. So A is row equivalent to I. Right? So A being invertible implies that A is row equivalent to I. And going in opposite direction, right? So if A is rho equivalent to I, how do I show that A is invertible? And this is where we're going to have to use our elementary matrices. All right, so if A is rho equivalent to I, right, that means that I can perform my elementary row operations in order to convert A to its reduced row echelon form, which is I. And if I'm using my elementary matrices to perform those elementary operations, then basically each time I perform an operation is going to be multiplication by each new matrix. So say like I did my first operation, maybe I eliminated some values below the first pivot. I can express it as multiplication by E1. Then I'm doing another operation, I'm multiplying it by another matrix and by another matrix and by another matrix. So doing my elementary row operations on A is basically just kind of like this long string of keep multiplying my elementary matrices by what I already have until I get to I, right? All right, so then I know that, say I had to do P elementary row operations in total. And all of this could be described as this multiplication of my elementary row matrices times A. Now, and what I get from there, so one thing we know, all of my elementary matrices are invertible, right? So we did that example where I can just kind of like undo each one, right? If I'm adding something, I can subtract, right? If I'm multiplying by something, I can divide by something. So all of those guys are invertible. And from that theorem we did last time, if two matrices are invertible, then the product is also invertible. So the product of all of those invertible matrices is also invertible. So we'll just use this fact here. Now, so because the product is invertible, just look at it at one matrix, right, that has an inverse. What I can do is I can take my equation I have, right? So multiplication of elementary matrices by A, which equals to In, and just multiply this on both sides by the inverse of this product of elementary matrices, right? So multiply by inverse, then what happens by definition of inverse now, this product is going to be my identity matrix, right? Because this is the inverse of that. So I have identity times A on the left, and on the right, I have kind of inverse of this product times I, right? So I is just like 1. So I times A is A, and this inverse times I is this inverse. So I'm getting that my A is the inverse of those guys. But then because this product is invertible, I can take an inverse again. So I'm taking inverse of both sides of this. And I'm basically defining what my A inverse is going to be, right? Because inverse of inverse is my original matrix. The inverse of this product, another inverse, is going to be my product. So I'm basically getting the formula for A inverse in terms of multiplication of my elementary matrices, which I obtained when I was converting my A to my reduced row echelon form of A, which was I, right? Because what was given is that A is row equivalent to I. Does that make sense? And again, that's why we did those elementary matrices, because it really just helps to figure out how do we get the formula for A inverse for any square matrix, right? So we're basically looking at how do we convert A to I, and at the same time, we're basically tracking how do we convert I to A inverse, all right? So that's kind of the proof of this, but I mean, we basically just have the algorithm for computing our inverses. And maybe you guys have seen this before in algebra. Probably didn't prove it, so we proved it now. But in practice, it's not that hard. You just have to remember to, if I want to find an inverse, what I'm doing is I'm basically forming my augmented matrix, except now I'm augmenting my entire identity matrix to my A. So in this case, I have my 3 by 3 matrix. I want to find an inverse, so I'm making an augmented matrix where my first 3 columns is my A, and then my last 3 columns is my I, right? So I'm putting together A and I into one matrix. And then I'm going to perform all of my elementary row operations until my A becomes I, right? This A is row equivalent to I, then AI is row equivalent to IA inverse, right? So that's kind of what we showed last time, right? So I'm basically multiplying all of my elementary matrices, because here to get A inverse, I'm actually doing the same sequence of operations, right? Except I'm doing those operations on my matrix I, right? So all of those operations I had to do to get I from A are all of those operations I have to do to get A inverse from I. Now, that's exactly what we're doing here, right? So I'm basically doing it on both A and I, and while I'm doing it on A, my I is slowly being converted to A inverse, right? So again, just look at the 3 columns of A and do all of the row operations that you need to do to convert A to I. Right, so like I'm interchanging row 1, row 2, right? Put 1 in the first pivot position, then I'm eliminating everything below that pivot position. Right, then I'm going to second pivot position, eliminating -3. Right, so just everything we've done before, right? And I know if A is invertible, I will be able to get I here when I'm getting my reduced row echelon form. So once I get 1s on the diagonal, I eliminate 3 and 2, with elementary row operations. And here it looks like I'm already getting my I. And once I get I here, it means I multiply all of my elementary matrices by A. But over here, what will be left is basically my I that was converted to A inverse. That makes sense? Yes. So we have a few homework problems on this. So I'll do it. I mean, you guys have done this before at some point, no? Okay, you do this in algebra sometimes, just maybe without proof. Does that make sense? Questions? Nope. Okay. All right. Everyone's good. So again, so all you have to do, make augmented matrix AI, perform your elementary row operations until you get I A inverse augmented. And from that A inverse, you can pull out your A inverse. That's pretty much it you have to do. Make sense? Not too bad. All right, so this last chapter we have to do for 2.3 is the last one we have for the exam. This one is not very long, but it basically just summarizes a lot of the things that we did with inverses and one-to-one properties and things like that. So, I mean, you can look in your book, and I would suggest, I mean, I don't know, if it's easier for you to write things down to learn, I mean, for me, it does help, like making little tables to kind of organize things in my head. All right, but your theorem was called the invertible matrix theorem. It basically has a bunch of statements and saying that for a square matrix n by n, all of those statements are equivalent. So to kind of list them all, I mean, one statement, A is invertible. A is invertible is equivalent to A is row equivalent to identity matrix. All right, so that's what we did just now. All right, so I can multiply my elementary matrices, each of which are invertible to A to get IN. Those two are equivalent. Also, that is all equivalent to A has n pivot positions. Now, so that one is also a little bit more intuitive, but maybe more so if you connect it with the equation AX equals to 0 has only the trivial solution, X equals to 0. Well, connection between those two, I mean, we basically just did, right? Because when we were converting our I to A inverse, remember my A is row equivalent to I means that A has n pivot positions. And because A is square, my pivot positions would always lie on the diagonal, right? So A will have n pivot positions, and that follows kind of equivalent to A being row equivalent to IN. So those are connected here. So then we have like two groups here. So one group, so equation AX has only the trivial solution, is equivalent to columns of A form a linearly independent set, and a linear transformation X goes to AX is 1-to-1. Right, so remember when we did 1-to-1 linear transformations, I mean, we connected basically all three of those together, right? So linear transformation is 1-to-1. So if for each B, right, in the range, the image is basically mapped by at most one X, right? So I can't have a B mapped by two different X's, right? And that was connected to our theorem that my homogeneous equation only has the trivial solution, right? Because each equation is going to have a unique solution. The homogeneous equation always has the zero solution. So if solutions are always unique, then the zero solution would be my only solution, right? And this is connected to A invertible because if A is invertible, then I have a unique solution by multiplying by A inverse. And then this guy is also connected to those two because columns of A form a linearly independent set, right? So if I'm taking columns of A and writing down my linear dependence relationship, I mean, that linear dependence relationship is equivalent to writing an equation AX equals to 0. And we know that AX equals to 0 only has the trivial solution. So in my linear dependence relationship, this linear combination of columns of A equals to 0 will imply that all of those x's have to be equal to 0, right? Only the trivial solution. And that would be the definition of my linear independence. So kind of those three are kind of intimately related here. The 1-to-1 property, linear independence of columns, and homogeneous equation only having the trivial solution. The other three here, we have the columns of A span Rn. Equation AX equals to B has at least one solution for each B, and linear transformation X goes to AX maps Rn onto Rn. So this was my onto property, right? Meaning that basically for each element in my codomain, I can always find an element in the domain that mapped to it. So I'm basically covering all of my codomain when I'm doing my mapping, right? So, and this was connected to that by basically the definition, right? So for each B in my codomain, I can always find an X that maps to it, right? So I can always find at least one solution. And the columns of A span Rn means that I can take any vector in Rn and express it as a linear combination of columns of A, right? Which is basically equivalent to this equation always having a solution, right? So like all those concepts are, well, those three are connected for general matrices. But what connects this group, because for general matrices, a transformation can be 1-to-1 and not onto, or it could be onto and not 1-to-1, or it could be 1-to-1 and onto, or it could be neither. Right? What's different here is I'm dealing with matrices that are square. For square matrices, those two groups, 1-to-1 and onto, will always be connected. And that comes from the fact that my pivot positions, right? So if columns of A span Rn, that means I have pivot position in every row, right? So for general matrix, having a pivot position in every row, right? Maybe I have pivot position here, right? I have some values, have pivot position here. But then maybe I'm missing a pivot position in the third column, and I only have pivot position in the next column, and then in the next column. All right, so here I have a pivot position in every row. Right? This would basically mean that my A is onto. Because if I try to solve equation AX equals to B for any B, right, B1, B2, B3, B4, having a pivot position in every row means that my equation would always be consistent, right? I'm never going to end up with row of all zeros and something not zero, right? So pivot in every row, my equation always consistent. All right, so always has a solution. So this is my group over here, columns of A span Rn, equation at least has one solution, and maps Rn onto Rn. The condition of one-to-oneness is a little different. So if this was my matrix A, this would not be a one-to-one transformation, right? So this one is not one-to-one. Why? Because for one-to-one, I need to have a unique solution, right? AX equals to B must have a unique solution for every B. Right? And in order to have a unique solution, what should my matrix look like? Can I have something like this? No, right? Because over here, I will have a free variable. And when I have free variables, I'm basically going to end up with infinitely many solutions. So for unique solution, I need to have no free variables. But what's nice about my matrix now is that it's n by n. So if the matrix is n by n, and I have a pivot position in every row, that basically forces it to also have a pivot position in every column. All right, so if it's n by n, my pivot position in every row would imply that my pivots are on the diagonal. Right, because it's n by n. So this is my connection between onto and one-to-one, which only works for square matrices. Does that make sense, guys? I mean, it's kind of like it's a confusing thing at first, but once you get it, it's a lot simpler. Because again, you have to remember that kind of like this row here, one-to-one, and onto is not in general going to be connected. But for square matrices, they are going to be equivalent because I'm kind of forced to kind of put everything on a diagonal. Does that make sense? So, I mean, there's proofs for all of these implications, but I think we will do some of them. But I think the most important thing is kind of understand it conceptually first, because there's a lot of kind of different statements and a lot of implications between all of those statements. But if you don't kind of grasp the idea of it, it's kind of useless, right? Like you just have to understand like how it all fits together conceptually first before you do all the proofs. Does that make sense, guys? Like with this connection between onto and one-to-one, how they're basically the same thing, only for square matrices. Like for square matrices, n by n, and a one-to-one is the same as onto. Make sense? I mean, it's because, you know, I can have something like this if matrix is not square. So A is onto, but not one-to-one. But for square matrix, I can't have onto and not one-to-one. It would have to be one-to-one. All right. And then we have, so what do we have left here? Of A is invertible, A transpose is invertible. We proved that before, right? Inverse of A transpose is transpose of the inverse. And then there's two more things. So remember when we defined our existence of the inverse, we said there exists a matrix such that I can multiply on the left or on the right to get I. But I mean, those two conditions say that, well, I don't actually have to check both. If I just have one, so if I find a matrix such that multiplication on the left gives me I, it has to be an inverse. Or if I find a matrix that if I multiply to A on the right, it has to be an inverse to get I. Right, so I only need like one or the other to really find the inverse. So we'll prove those here. I mean, they're not that hard to deal with, right? So if there is a matrix C that I can multiply on the left to A to get I, then A is invertible, or here we can show that this means that AX equals to 0 has only the trivial solution. So we're basically going from this statement to A of X only having the trivial solution, right? Which would imply that all of this stuff implies that A is invertible, right? And here it's not too bad because, I mean, basically this fact that there is a C that I can multiply to A on the left gives me I, this allows me to solve my matrix equations. If I have my homogeneous equation, AX equals to 0, I know I have this C, so I'll just multiply the C into both sides of the equation. C times A is I, so I'm basically getting the formula for X, right? C times 0 vector is 0 vector. And X will be my only solution here, because I'm basically solving this algebraically now, right? So this allows me to solve my system algebraically, similar to how I'm solving systems with just real numbers, right? Not vectors. And the other condition, if I have a matrix that I can multiply on the right to A to get I, right, I can show that this implies that equation AX equals to B has at least one solution. So it's kind of like this one is connected to one-to-one property, and this one is more connected to the onto property, right? So if I have a matrix that I can multiply on the right, then equation has at least one solution. Well, I know that identity matrix times any vector B, not N, is B, right? And instead of identity, I can write AD because I know AD is I, right? But then if I use associative property, I'll multiply D times B first and then times A equals B. Then what I'm getting, I'm basically kind of writing down my possible equation, right? I'm trying to look for, does the equation AX equals to B has at least one solution? But then this is exactly in the form A times something equals to B, right? D is defined, B is defined, D is n by n, B is n by 1. So this multiplication is defined. So this is a defined quantity. And I know by construction that A times this quantity equals to B. So D times B basically gives me one possible solution. So at least one solution, X equals to D times B exists. All right. So again, kind of this condition here gives me that I should have at least one solution for non-homogeneous problem, which is equivalent to onto property. This guy here tells me that my trivial equation only has the trivial solution, which basically is equivalent to one-to-one property. And this is equivalent to onto property. That we already know that those two are connected when matrices are n by n. So we're kind of connecting everything together now. Maybe we can do one more. Some of them we've already proved in previous chapters. I just kind of did the ones that we missed just yet. So another implication we have, if A is n by n and homogeneous problem only has the trivial solution, All right, so this is this condition here that's connected to one-to-one property. And A, we want to show that this implies that A has n pivot columns and A is row equivalent to IN. All right, so with pivot columns, we already looked at it, right? So if this implies A is one-to-one, my equation X equals to B has a unique solution for all B and Rn. I mean, this is just definition of A being one-to-one. So because this is true and we have a square matrix, I do need to have pivot position everywhere in a diagonal, right? Because then this will give me first X, second X, right? Each X is uniquely determined, those pivot positions, right? I have n pivot positions. This is row equivalent. This means that A is row equivalent to I, right? Because it has n pivot positions. I has n pivot positions. That's basically it. So you guys good, comfortable with all of this? So I know it's kind of a lot, but yeah, maybe just sit down, kind of write out all your theorems, kind of try to kind of convince yourself and the connections. But like the main connections here are basically those three, one-to-one, those three are onto. Those two are connected through the fact that A is square. And then you can basically connect a lot of those pieces back to kind of row equivalents to I and having n positions, right? And things like that. And those two are connected to one-to-one onto. So all of the statements are basically equivalent, right? Any one of them implies the other one. So to show that A is invertible, basically, all you have to do is show one of many of those things. If one of many of those things holds, then A would have to be invertible. And if A is invertible, then all of those things hold. And with that, basically all of our n by n matrices are going to be either invertible or non-invertible. Right? There is no other option. Either A inverse exists or A inverse does not exist. And again, main thing is always just for square matrices we're dealing with here. Any questions, guys, so far? You know, this chapter is kind of like a lot of theorems. But we'll get the applications. We have just one more theorem here. All right, so before we showed that we showed that if A and B are invertible, the product is invertible. Now, but here we're doing something a little bit different. We're saying that if I have two square matrices, the product of those matrices is I, then, so I don't know if they're invertible yet. I just know that the product is I. But if this is true, then this implies that both A and B are invertible. And not only that, they're actually inverses of one another. So B is in the inverse of A and A is in the inverse of B. All right. And you can kind of show all of this. All right. So if AB equals to I by definition of the inverse, if I can find a matrix B, I mean, in our, what was our theorem? Remember those two parts of the theorem we had? Right. So if I have a matrix that I can multiply on the left, or if I have a matrix that I can multiply on the right. So over here, I can find a matrix B such that AB equals to I, right? So this is this condition here. This implies that A is invertible, right? And because A is invertible, I can multiply by A inverse on both sides. A inverse times A is I have inverse times I equals A inverse. So then B must be equal to A inverse. And that makes sense? All right. And the other direction for B, here I'm using this condition. If there is a matrix that I can multiply to another matrix on the left, then A is invertible. So over here, I can find a matrix A that I can multiply on the left to B to get I, which means that B is invertible. And then because B is invertible, I'll multiply both sides of this by B inverse. Then A times B inverse, B times B inverse is I times B inverse is B inverse, and then A times I is A, and then B inverse is just B inverse. So I showed that A must be equal to B inverse. That makes sense? So I mean, that also illustrates how you know, if you want to justify some theorems or proof theorems, that's kind of how you do this here, right? You have to use the theorems that you already know and go from there to show some new facts, right? So again, here we showed that if I just have two square matrices and I multiply them and I get I, that means that they're going to be both invertible and they're going to be inverses of one another. So B is an inverse of A and A is an inverse of B. Now with that theorem. So what else? We're almost kind of done with this chapter here. Like I said, it was mostly just a lot of the theorems. So I mean, in general, how can we tell if the matrix is invertible? I mean, for general case, to be able to tell if matrix is invertible, I mean, unless you already like trying to look for an inverse, what you can do is, I mean, try to bring it into row echelon form. I mean, not even necessarily reduced row echelon form, but at least to row echelon form, because once you kind of get an idea where your pivot positions are, you would be able to say if your matrix is invertible or not, right? For invertibility, you need to have all of the elements in a diagonal need to be your pivots, right? So if A is n by n, you need to have 3 pivot positions. All right, so A, n by n, you need n pivot positions for A inverse to exist. All right, so once you kind of get a hang of your pivot positions, if you have all n of them, then your A is going to be invertible. All right, so if you just want to answer the question whether it's invertible. So you do have to do your elementary row operations. But some shortcuts, I mean, you can kind of look at some. So if I look at this matrix here, I have 2, 2, 2, 3, 3, 3, 4, 4, 4. Right, so I have my columns of this matrix are going to not be linearly independent, right? They're basically all multiples of another, right? So because my columns are all multiples of one another, columns are not linearly independent. And if columns are not linearly independent, I can again go to my theorems. I need to have linearly independent columns so that I have a one-to-one transformation, so that I only have unique solution to homogeneous system, so that my A has n pivot positions. So if my columns are not linearly independent, I am definitely not going to have n pivot positions. So, and here you don't have to do very much more work. Right, you can just conclude that A is singular. Right. Or the other case, columns linear independent, the other case could be if my right, so if I look at this matrix here, 1, 2, 3, 2, 4, 6, minus 1, 0, 7. Columns look okay, at least at the first glance. But if I look at my rows, row 1 and row 2, my row 2 is twice row 1. Right. So my rows 1 and 2 are multiples of one another. So what will it give us when I start doing my elementary row operations? I'm basically going to end up with a row that consists entirely of zeros, right? So my A would be equivalent to a matrix where one row is entirely all zeros, right? If I just subtract like twice row 1 from row 2, I'll get a row of entirely zeros. And if I have a row entirely zeros, I am missing a pivot position. I'm missing a pivot position. Another way to look at it, my matrix A is not going to be an onto mapping, right? Another way to look at it is I'm going to have inconsistent systems when I try to solve AX equals to B. I might not have a solution for every B. All right, so a lot of things can kind of follow from the fact that my rows are linearly dependent. All right, so again, here I can immediately conclude that A is singular. All right, so kind of those two examples, if you notice that either my columns are linearly dependent or columns are multiples of one another, or my rows are multiples of one another, or I have a row of all zeros, then A would have to be singular, right? Because here I'm not going to be onto or one-to-one, right? So again, if you can notice something like this, you don't have to kind of go directly to your row echelon form. But I mean, if you do this, you have to, label on your homework or on your exam, why you're making that conclusion. That makes sense? Yeah, not too bad. Is there any questions so far? No? All right. All right, so I mean, and the last thing here, I mean, this chapter was, again, mostly just kind of organizing everything we've learned about kind of inverses, matrices, and linear mappings. And we've been working with matrices, but again, remember, matrices and linear transformations are basically the same thing for us here. So if I'm now kind of trying to translate everything in the language of linear transformations, it's basically the same thing, right? So if my matrix A maps X to the range AX, I can basically look at it as linear transformation T, or I can look at it as multiplication by matrix A. All right. Or if I'm doing an inverse matrix, an inverse matrix basically transforms everything back, right? Because A inverse of A or A times A inverse is going to be identity. So my inverse transformation is basically going to be multiplication by inverse, or my T inverse is my opposite transformation. Or inverse of inverse is inverse, so S inverse is going to be T. So I'm just translating kind of my matrix algebra into language of linear transformations, right? And you can kind of rewrite all of those theorems in terms of transformations, like a linear transformation is invertible if there exists a function S such that S applied to T is going to give you X back for all X in Rn, and T applied to S is X for all X in Rn. I mean, this is basically equivalent to our matrix definition, because remember, we defined multiplication of matrices as compositions of linear transformations, right? So here would basically multiplication by C is my S, right? And either I'm applying C to A, S of T is going to be C times A, or I'm doing A times C times X. I'm just rewriting this in terms of linear transformations. But otherwise, everything is pretty much exactly the same, right? And we can rewrite all those theorems, but I mean, we're not gonna do this here. Well, just one. So if I let T be a linear transformation and let A be the standard matrix for T, so T is basically a transformation that multiplies vector by A. Then T is invertible if and only if A is invertible, right? So it's the same thing. And in this case, a linear transformation S multiplication by inverse is the unique function, right, satisfying those two properties. So it's basically just a restatement of what we did for matrices, but kind of introducing a different notation of the linear operator, with the linear transformations. And because my T maps X to AX, my T inverse maps Y in a range to A inverse times Y. So inverse times y equals to x. Not, and kind of all of my relations, a times a inverse times y is y, a times a inverse times a times x is x. Now I'm just rewriting it in terms of my linear transformations. Does that make sense? Right, so we're not gonna redo all of the theorems just because the notation changed a little bit, but again, we're just looking at matrices as an application of linear transformation. So all of those things hold, even if you talk about it in terms of linear transformations and not just multiplication of matrices. Make sense? Questions? Well, finished 2.3 here. So as far as your exam goes, we're basically done. Like everything past that is going to be on the next exam. But any questions on the stuff we just did? You guys are all quiet today. No,
No, I don't think I have any questions. Everything makes sense.
yay, someone is alive. I'm not alone. Like when no one is talking, sometimes I'm like, is anyone even there?
No worries. I'm always here. I'm listening.
Yeah. That's good. All right. So you guys are good, comfortable with all of this? Your exam is on October, so it's due in October. Not, yes, you have like, you have plenty of time. So like next week too, if you guys have, so if you look, well, once you look over this homework, if you guys have questions, I mean, maybe we can do a little review for everything so you can prepare for the exam. Right, and we'll do that next week. Yeah.
Will you have everything posted that you've gone over today, later today or tomorrow?
Yeah, so I'll post the notes and I'll post the video. I'll post like the
Okay.
YouTube. I'll download this and I post it as a YouTube video.
Okay. Just wanted to be sure. On the test you did earlier today, described 9 questions will be on there. Will you
Mhm.
say similar to the quizzes that we've experienced in terms of difficulty?
I mean,
Or
I
would
think some of them are maybe shorter because like there like would be like some questions kind of asking something along the lines of kind of what we did here. So there could be a question being like explain how like an onto property is equivalent to one-to-one property if the matrix is a square matrix, right? So you just have to kind of explain it a little bit.
okay. So
Yeah.
it's going to be more test your theory, not test like a hard problem
I
on
think
you.
there may be like two problems where you have to explain things. And then
Okay.
there's problems like, like determine if like some vectors are linearly independent or like but I mean, it's going to be very similar to your quiz problems. I mean, not exactly the same, but yeah, it would be, I guess your homework problems, how are your homework problems on the online?
A little weird sometimes, but pretty
Yeah,
straightforward.
I was kind of looking through them the other day and they were like, oh God, like the multiple
There was a
choice ones.
There was a few that took a few attempts, but
Yeah.
nothing hair pulling.
Yeah, I mean, they're not bad problems. It's just kind of like the format. You have to explain something, but you're not really explaining. You're just like reading through different statements, choosing which one.
No, I'm not a fan of stuff like online programs that teach you math. They never work really.
Yeah, I mean, me either. It's just, it takes a long time to grade everything. Um,
Yes, I understand.
so I'm trying to do quizzes. Um, Well, the good thing about the online part is that you kind of get the instant feedback. So if you did something wrong, like it'll tell you, and you can fix it. Like if you submit stuff on paper, like you could have done something wrong and then you just don't know. Um,
Mhm.
Unless you like work together with other people or know the answers. Yeah. Maybe I'll try. Maybe I'll do. Well, if I have, I don't know if I have time, maybe I'll like post some kind of like a practice, like a few practice problems or something.
That would be amazing if you can.
Yeah, I do. But otherwise, like, if you go through like the lecture notes, like the examples I do in lecture notes and the quizzes, I mean, you should be okay. But I'll post some addition like, if I have time. I can't promise. It's kind of been
No, no, you're fine.
yeah. If I have time, I'll do it. I'll try. Yeah, I think yeah, no, like I mean, I usually do like practice problem sets for classes. Just this semester has been a little busy, but I'll do my
Have you
best.
posted the answers for the previous quizzes?
So I've been sending them
Yes,
as I'm
yes.
grading. So like if I grade your quiz, I'll send it. But I'll go through them today and I'll post them in the modules. So I think quiz one solution is posted.
Yes, I know I believe that was the only one that had a solution.
Yeah, so I'll go like the quizzes that are past due, I'll post the solutions today to all of them. And then maybe
That would be fantastic.
the ones that's not past due yet, maybe I'll just email everyone who has submitted it. I'll email the solutions so you guys have everything.
Okay.
Yeah. All right. So I have like 13 minutes. Maybe I can get a jump start on next week's stuff. So we are going to skip some chapters. So we finished 2.3 and then we're going to skip basically everything between 2.3 and so we're gonna jump to 2.8. So like the chapters in between that, there's like partitioned matrices and some other applications. They're good chapters. Like if you can read through them, but I mean we don't have that much time to, I kind of have to like pick like the most important chapters for us to cover this semester. And I looked at and I saw other professors are skipping those in Palomar College as well. So that's why kind of we're gonna skip those, but you guys can read through them. They're just kind of more specialized, how to deal with partition matrices and things like that, but not kind of like essential material. All right, so we'll skip to 2.8. So we'll start talking about what's called subspaces of Rn. All right, so that's kind of like a very like core of linear algebra. Like if you take like upper level linear algebra classes, you normally just start with the subspaces. All right, so what is a subspace? So a subspace is basically kind of like this definition of a set of different vectors, but it has to satisfy particular properties. So the subspace of Rn is any set H in Rn that has the following three properties. So the zero vector has to be in the set. Right, so if you're thinking of it kind of geometrically, right, the origin has to be in H. And the only other two properties is that your set has to be closed under addition, which means that if I have two vectors already in my set, then the sum has to be in that set. And it has to be closed under scalar multiplication. So if I have a vector in H, then C, any real number C times that vector should also be in H. So it has to be closed under scalar multiplication. Right, so if those three hold, then I'm going to call my set a subspace. Right, so if UVI in Rn, then it's a subspace of Rn. Right, so and we'll do some examples of this. Right, so kind of the basic way to construct such a set or subspace is just to start taking spans of different vector sets. So if I have two vectors in Rn, and I'll define my H as span of those two vectors, it will be a subspace because, well, for one, does zero belong to span to two vectors? Then yeah, because what does it mean to belong to a span of two vectors? That means that I can express this as a linear combination of v1 and v2. And zero vector, well, I can just do 0 times v1, 0 times v2. linear combination of V1 and V2, so 0 is there. Good. Second condition, closed under addition. So I have two vectors already in a span of V1, V2, right? That means that U is a linear combination of V1 and V2, and V is a linear combination of V1 and V2. So I have some constants multiplied by vectors. When I take the sum, right, I have my U, I have my V, but then I just have constant V1, constant V2. So alpha 1 plus alpha 2 times V1, I'm just factoring out, right, V1. And beta 1, V1, and beta 2, oh, this should be 2. Oops. All right, I'm factoring out V2. So if I rearrange and simplify, I'm basically again getting some constant times V1, some constant times V2. So the sum of those two vectors is also a linear combination of V1 and V2. So it's in a span of V1, V2. So I'm closed under addition. And then scalar multiplication also, because I can always distribute constant. So I still end up with constant times V1, constant times V2, which is in the span of V1 and V2. Right, so a span of any number of vectors is always going to be an example of what's called a subspace of Rn, because it will be closed under addition, closed under scalar multiplication, and the zero vector will always be in a span. Right, so, but then the question is, well, wouldn't everything then be a subspace of Rn? And no, not really, because, well, for the previous example, I mean, there's actually a couple options here, right? If I'm taking span of two vectors, if those two guys are linearly independent versus when they're linearly dependent, my subspace is going to be a little bit different, right? So for example, if my vectors were in R2, for example, if my V1 and V2 were in R2, all right, then if they were linearly independent, they would be spanning a plane. But if they were linearly dependent, then since V1 is multiple of V2, they're actually spanning just a line, right? But in either case, right, so if I just consider the case when my subspace is just the span of one vector, the span of one vector is still going to be a subspace, right? 0 is in the subspace. Any multiple of that vector is in a subspace along the line. And then if I start summing up V1 and V2, right, or V1 to itself, I'm still going to be everywhere along this line, right? So I'm closed under addition. So a line through the origin is going to be an example of a subspace, right? But if I take the line that is not through the origin, it's not going to be a subspace. I mean, for one, 0 is not on my line. So 0 is not an element of H. But also I'm not closed under addition, I'm not closed under scalar multiplication, because say, if I take those 2 points on the line, say this is vector V1 and this is vector V2. If I add V1 and V2, I'm going to be off the line, right, using my parallelogram rule. So the sum does not belong to L. So I'm not closed under addition. I mean, also, if I start taking scalar multiples, like if I took twice V1 or something, that also puts me off the line. All right, so I'm not closed under scalar multiplication. So again, I have line, but in this case, this line is a subspace of R2. But in this case, this line is not going to be a subspace of R2. So I mean, the first thing to look for is, like, I definitely need to have a 0 in my subspace. So if I have a line or a plane that's not through the origin, it's not going to be a subspace of Rn. So you definitely always need to have 0 in there. And then you can check closed under addition or closed under scalar multiplication. That makes sense? So I don't know stuff about this. But in general, when we're taking the kind of span of a bunch of different vectors, I mean, this is going to be a subspace, because 0 is always going to be in a span. I can just take 0 coefficients when I'm taking linear combination. And then since I'm doing span, it's all linear combinations. So if I start adding, subtracting those vectors, it's going to be just another example of some linear combination of them. So it will be in a span. And so is with scalar multiples, right? So span of any vectors, right, would be linear set of all linear combinations of those vectors. It will always be a subspace of Rn. Right, and we'll call it the subspace spanned or generated by those vectors. Right, and we can prove a little bit like 0 is always in the span. We talked about, I'm just using summations because now I have a kind of arbitrary number of vectors here. Right, sum, right, just like in the previous example we did for 2 dimensions, we'll have basically sums of constants for each one and scalar multiplication. So this is always going to be a subspace. And some special subspaces, so Rn itself, remember when we're dealing with subspaces, we're looking at, so P does not have to be equal to N, right? So we're looking, P is the number of vectors, right? So in Rn, to say if I'm in R3, Rn is kind of my embedding space, right? But the number of vectors, I can have like 10 vectors in R3 and they span R3, or I can have 4 vectors or 3 vectors. If I have 2 vectors in R3, are they going to span R3? That now you guys should know by now. But we'll get back to it. So I mean, we do need to have P at least equal to N or more if we want to span the space. But in general, your H is just going to be some, maybe like a plane in R3 or something like that, right? But sometimes you can have vectors that span the entire R3. So Rn is a subspace of itself, right? And we also have the smallest subspace we can have is the 0 subspace. So 0 subspace is basically just the origin, right? And I mean, it's trivial, right? I mean, the first condition holds 0 is the only element of that subspace, but also those two guys hold because, I mean, U and V have to be elements in the subspace. I mean, this one only has one element, so really the only sums I can have is like 0 plus 0, C times 0. So I mean, it also holds, right? So we kind of have, in Rn, we have cases of subspaces. I could have Rn, the entire Rn, I could have something in between, and the smallest is I could have 0, right? So different cases. Well, maybe I'll leave this until next time. So we'll do that definition of subspaces. So we'll look at some examples of subspaces next time, and kind of like those 2 examples will be column space and null space. All right, so this would be again related to solutions of our linear systems, like column spaces. If I take all of the columns of my matrix A and take the span of those columns, this would be the column space of my matrix, right? And null space would basically be kind of a set of vectors that span the solution set of my homogeneous equation. We're kind of out of time today, but we'll do that next time. We'll learn how to find them. Then we'll talk a little bit more about subspaces. But yeah, we'll leave this until next time. Well, got a little jump start. So you guys have any questions? Yes, no, everyone's good.
No, everything makes sense. Thank you, Professor.
Okay, cool. So I will, I'll post the notes for today. Your homework on my MATLAB is posted already for this week. So I'll do that. There's no quiz since we're gonna do a midterm. And actually, I mean, if you guys want to start midterm earlier, it's due October 9th. But I mean, I can make it open earlier too. I mean, it doesn't matter. Cause I mean, once you open it, you have to submit it in 4 hours. So like October 1st, I'll make it open. So yeah, otherwise, if you guys don't have any questions, I'll see you next time. And yeah, and I'll post the video in the module for today. All right. I'll see you
Thank you,
guys.
Professor.
Yeah, no problem.